Hello everyone. My name is Anvesh Kumar, and under the subject linear algebra, I will be covering the topic rectangular system of linear equations. And in this topic, I will be covering the headers of least square method, minimum norm method, and pseudo inverse. So for the topics that I will covering, I will be talking upon what is the problem with rectangular system of equations and when these rectangular systems of equations will have a solution, or if they do not have a solution, like mostly in overdetermined system we do not have a solution, so how do we find approximate solutions for them? And I will generalize the solution with a single formula using SVD, and I will also give some examples of use of rectangular systems. So let's start. So there are two types of rectangular system. So basically, what is a matrix? A matrix in our system of linear equations, we will have m equations, m equations with n variables. So if the m is larger than n, then it will be longer while being the width being smaller. Those type of systems are called overdetermined, in which we have more number of equations than number of variables. So this type of system is common in applications where there is an excess of information or constraints. These type of systems generally don't have an solution, so we find its approximate solutions generally using the methods of minimizing the error. The second type of system of linear equations are underdetermined system. These are a system in which there are less equations, number of equations than the number of variables. So clearly we can see that if we don't even have that many of number of equations, as much we have variables, we will not have unique solutions. We will have infinite solution. Such systems arise when there are insufficient constraints to uniquely determine all the unknowns. We need additional constraints and criteria to find its optimal solution. So to find the optimal solution for our underdetermined system, we generally use constraint optimization. Okay, so what is the problem with rectangular system? That we have to do certain different things for it. So when we are talking about linear equations, we are talking about something like Ax equal to B, where A is a matrix which maps our x to B. So in our questions, we know A, which is determined by the system which we are applying the linear equations to, and we are given B, which is a resultant matrix. And for using these two, we are solving for x. So when A matrix is a square matrix, and we can see that there will be a solution for x, we can directly find out x by using A inverse B, because A inverse will exist for the square matrix. But what if our A matrix is rectangular? We can't find its inverse like we were doing for square matrix. So different methods that we can use now is that we can approximate its solution when we do not have a solution, like in underdetermined, like in overdetermined systems, or we can find the optimal solution like in the underdetermined system using minimum norm method, or we can generalize this for rectangular system using SVD. Okay, 1 second. So we know that underdetermined systems will have infinite solutions or no solution. It can also have unique solutions, but that will be a very rare case. For that, we have to apply some external constraints, like some condition that solutions must be this. So all the rest solutions gets cancelled out, and a unique solution is only left. So, if it has unique solution or not depends on the external constraints. For example, in real world scenario, there may be physical constraints or practical limitations that limit the possible solutions. For overdetermined systems, we generally have zero solution. So for finding their solution, we have to find approximate solutions. But in certain cases, of course, there you can think of some certain situation in which they have solutions. Example, this 2x plus 3y equal to 10, 4x plus 6y equal to 20, and we can see the third equation is the linear combination of these two. So basically, uh, this can be seen as two equations, two variables, because third equation don't have any value. So we can generalize this to formulate a law, to formulate a condition for which our system of linear equations will have a solution. So we know that when ax equal to b and a is something like c1, c2, c3, where c1, c2, c3 are its columns, then b can be represented at x1, c1, x2, c2, and so on. So basically, when if it has a unique solution, if x has a unique solution, then this must exist. So we can say that if there is an if a unique solution exists, b should be in the column space of a, as b can be represented as the linear combinations of its columns. Also also uh, for infinite solutions, if dimension of null space of a is not equal to 0, which means certain element in the null space exists other than 0 comma 0 comma 0, then there will be infinite many solutions. We can see this directly as if ax equal to b, then ax plus x null will also be equal to b, as ax will be b and ax null will be 0, and ax plus 2 into x null will also be b, and so on, so on. So we will have infinite solutions for them. So let's start our topic, least square approximation, which we do for overdetermined systems to find an approximate solution. So how do we go about that? So least square method, what it does, it finds out a solution for which the this equation ax minus b, the L2 norm of this will be smallest. Least square method find out a x for which ax minus b, L2 norm of ax minus b will be the smallest. So to calculate this, we formulate a error function or residual function, which is phi x. Uh, so we use a property that L2 norm of any vector, square of L2 norm of any vector is R transpose R. So we apply this on ax, L2 norm of ax minus b. Square of L2 norm of ax minus b can be represented as this, and this is a residual function. So to minimize this, we can minimize our residual function phi x. So to minimize this, we find out, we differentiate it about x, and after differentiating, so basically our residual function was this, and we it has two terms in between this and this, and we can see that if our equation was ax equal to b, let a be of order m cross n. So x has to be order of n cross 1 and b has to be order m cross 1. So see here, x transpose will be of order 1 cross n, a transpose will be order of n cross m, and b will be of order m cross 1. On multiplying these matrices, we can see the order will be 1 cross 1. Or we can say this is a scalar. Similarly, you can see this is also scalar. uh, and we can also see that the second term is the transpose of first term, and these two terms are transpose of each other and are also scalars, so we can say that these two are the same thing. So as these two are same thing, so we further transform the equation into this, that our residual function is equal to half of x transpose a transpose ax, which comes after breaking up the brackets, minus 2 times x transpose a transpose b plus b transpose b. Now we have to find the minimum x for which this exists. So we differentiate our residual function about x which comes out to be this, and we equate it with 0, and this will give us our optimal x, or the x for which there is a least square. We see that our least square approximation comes to be A transpose A inverse A transpose B. And this term, A transpose A inverse A transpose, is called the right pseudo inverse. And we represent it by A plus. Okay, so for overdetermined, we solved our equation. So for overdetermined, as we didn't have, as for overdetermined system, we didn't have any solution. So we found out a solution for which there will be a least square error. So, what is least square error? That ax minus b, L2 norm of ax minus b will be minimum. So we found out a x for which this will be minimum. And now in underdetermined system, what we do? In underdetermined solution system, we know that there are infinite many solutions. So we try, as there are solutions possible. So we have to find a optimal solution. What will be that optimal solution? That optimal solution will be that which have minimum this. Optimal x will be that which have minimum L2 norm. All right. So we have to find out the x which have minimum L2 norm. And how will we do this? We will do this again by the same method, by applying constraint optimization and then differentiating about the two variables that it has. A note is that we cannot apply least square method on underdetermined system. We can see that A is, let A be a M cross N matrix, and for underdetermined system we know N is N is greater than M. So in least square error method, we were calculating a right pseudo inverse, which is this. So we can see from here that A transpose A will be N cross N matrix. Yeah. And we can see that rank of A will be less than equal to M, as the rank is less than equal to minimum of number of rows and number of columns. So we can see that rank will be less than equal to M, as minimum here is M, which is the number of rows. Rank of A will be less than equal to M. And so if rank of A is less than equal to M, rank of A transpose A will also be less than equal to M. This is a theorem. And our matrix was of n variables, and its rank is coming out less than M. So it is sure that it has some it is rank deficient. And if it is rank deficient, its rank is if it is rank deficient, its inverse does not exist, as A transpose A will be a square matrix whose determinant will be 0. So its inverse would not exist. So we cannot apply least square method here. So moving on, we will calculating the minimum norm solution. So to calculate minimum norm solution, what we have to do is that we have to minimize this, the square of L2 norm of x, while satisfying the condition ax equal to b. So we make a loss function, which is a Lagrangian, which is half of x transpose x, which is basically deconstructing this. This can be written as this, x transpose x. L2 norm of x can be written as x transpose x. And this is a Lagrangian multiplier, which basically adds on a constraint, additional constraint. We had to add this constraint. We applied this using this Lagrangian multiplier. So, so these are what. So these are our two conditions or constraints which we are going to apply. So we differentiate our Lagrangian with respect to x first, which comes out to be this. Now notice that x transpose x will be a scalar. As you can see, x will be a something like this, and x transpose will be something like this, and its product will of course be something like this, which will be a scalar. All right. So if this is a scalar, we choose our mu transpose such that this will also become a scalar, because only scalar can be added to a scalar. So this is a scalar and this is a scalar. So what we do is we take transpose of this and then differentiate with del L by del X. Uh, so without taking transpose, our equation was this. So if we take transpose of whole equation and then differentiate with partially differentiate with respect to s, we will get the opposite solution of this x star plus a transpose mu. All right. So this will be our equation, and x star will come out to be minus a transpose mu star. So this is our first equation. Now we differentiate our Lagrangian with respect to u, and that comes out to be this equation. And then we put our x star here, which convert this to this, and from this we calculate our mu star, and again put this in our first equation, which will give us this, and our final results come out to be this. So this is the x star. This x star represents that x which will have the minimum norm. All right. And this thing which we have here, a transpose inverse, this is called the left pseudo inverse, as it is on the left of B. It is just a nomenclature. And it is also represented with the A plus. So moving on, let's solve a question based on this. So first of all, we solve a least square method. First solve a overdetermined solution using the least square method. Hmm. So what was the formula which we finally got in the least square method? That was this. That to find out our least square solution, we have to use A transpose A inverse A transpose multiplied by our B. So first we calculate our A transpose A, which comes out to be 3, 3, 3, 5. Then we calculate our A transpose A inverse, which comes out to be 1 by determinant of this, which is 15 minus 9, 6, and 3, 5, minus 3, minus 3. So let's calculate this term. Comes out to be 1 by 6, 3, minus 3, minus 3, 5, multiplied by A transpose. Is A transpose? A transpose is 1, 1, 1, 0, 1, 2, multiplied by B. What is this? 6, 0, 0. It comes out to be 1 by 6 times by 6 times. Oh, sorry, I did a mistake here. A transpose A inverse will be we A transpose A will be this 5, 3, minus 3, minus 3. All right. Let's change here to 5, 3, minus 3, minus 3. So our solution will be 5, 2, minus 1, minus 3, 0, 3, 6, 0, 0. And on solving this, we will get 1 by 6 times 6 times 5, comma 5 and minus 3, and this 6 is 1. So our least square solution comes out to be 5, comma minus 3. All right. So x1 will be 5, x2 will be minus 3. So what we mean by this solution? We mean that this will give the least square solution, which means this will give the minimum value for ax minus b. What will be the L2 norm of x minus b? What will be that value? Let's calculate. What was our A? Our A was 1, 1, 1, 0, 1, 2. Let's multiply this with our x 5, minus 3, minus b 6, 0, 0. It will be 5, 2, minus 1, minus 6, 0, 0, equal to minus 1, 2, minus 1. L2 norm of this will be square of L2 norm of this. So we square of L2 norm of this is equal to under root of minus 1 ka square plus 2 square plus minus 1 square equal whole square equal to 6. So this will be the minimum square of L2 norm, square of this thing for all the x possibles. This x will be the optimal one. Now let's move on to solve for underdetermined systems. So this is an underdetermined system, and we can clearly see that it will have infinite solutions. For example, 1 by 4, 1 by 4 half will solve this, 0, 1, 0 half half will solve it, half 0 half will solve it, and many more. So what we have to do among all these solutions, we have to find that solution which will have the minimum norm, which is this. Which we have to find a solution which is a minimum this. How will we do that? Uh, we will do that by using that formula that we have derived. What was that formula? A trans 1 second. For underdetermined, our minimum norm x comes out to be A transpose A transpose inverse multiplied by B. So let's calculate that. What is our A? First, let's mark our A. A is 1, comma 1, comma 1, minus 1, minus 1, 1. So A transpose will be 1, 1, 1, minus 1, minus 1, and 1. This is our A transpose, and we have to calculate A transpose multiplied by A transpose inverse. So let's calculate first A transpose. On calculating, we know we come up this comes out to be 3, comma 3, comma minus 1, comma minus 1, and multiplied by its 1 upon determinant, which comes out to be 1 upon it. All right, and this is A transpose. No, no. This comes out to be A transpose, and now what we have to do, find its inverse. So A transpose inverse comes out to be 1 upon determinant of this 3, 3, and we change the signs of this 1. This is A transpose inverse, and this is A transpose. So we can simply find out our minimum norm x, which will come out to be 1, 1, 1, minus 1, minus 1, 1, multiplied by 1 upon 8, 3, 3, 1, 1, multiplied by b. What is our b? 1, 0. Let's calculate this. Yeah, so let's calculate this. This whole thing comes out to be 1 by 4, 1 by 4, half, minus 1 by 4, minus 1 by 4, half, and let's multiply with 1 by 1 and 0, which comes out to be 1 by 4, 1, 1, 2. So our optimal x, minimum norm x will be this. So we solved for overdetermined system and found out a solution which will be a least square error. And we also found out a solution for a underdetermined system, which will have minimum norm. What is surprising is that these both methods could be generalized. How? Using SVD. So we know that SVD gives a breaks down A into three different matrices, and we can find out a pseudo inverse you by finding out inverse of these. All right. So the pseudo inverse which we get using SVD, which is this, will be the least square error in case of overdetermined system, and will be the minimum norm solution in case of underdetermined system. It is so generalized, which is surprising. And we can calculate this like this, in which we break down A into U sigma V transpose, and then take its inverse, both side we multiply by its inverse. So it gets multiplied like this: V sigma inverse mu transpose into mu sigma V transpose. So mu transpose mu convert to identity matrix, sigma inverse sigma convert to identity matrix, and V transpose convert to identity matrix. So here we have identity matrix, and that side we have an inverse of it. So if A is this, A inverse is this. All right. And this is called the Moore-Penrose pseudo-inverse. And what is surprising about this is that if we for a overdetermined system we calculate this, it will give the least square solution. And if for underdetermined solution we calculate this, it will give the a minimum norm solution. And if for square error, it will obviously give the solution, real solution. So if A is rank deficient, which means A transpose is not invertible, then we cannot apply the above formulas in which we are using A transpose inverse or A transpose A inverse. Those formulas will fail, but this method will still apply. So use of SVD is extremely helpful here, and this is surprising how this gives the same result as the result we calculated using uh, differentiation and constraint optimization. So this is all of the calculation that was in this topic. I can also give you some examples where rectangular systems are used. For example, in data fitting and regression, we we all know in regression, uh, linear regression, we also have that problem where we calculate the minimum square error for all data, and we tend to minimize that. There also we have the same problem. There we get use of rectangular systems. In image processing, of course, in image we split our images into um, matrices by splitting it into pixel values, and there we usually don't have a square matrix. We usually have a rectangular matrix which we have to use pseudo inverses to calculate its inverse, to manipulate it, to change it into another image, and etc. etc. It is also used in signal processing, and also machine learning and neural networks, where training a neural networks involves solving a system equation where number of equations might not match the unknowns. All right. So this was all from my side on the topic of rectangular linear systems. Thank you.